Modifying Newton's approximation into nonlinear formulas. Reviewing Newton's linear approximation, we have this graph and this curve, f of x. And the point that we know is xo, yo, and we call it point A. And the point we want to know is point B, and that's xy. And from Newton's linear approximation, usually what we do is we draw a tangent line from point A, and it will hit the vertical line at when it's equal to x. And this is now approximated by this triangle. And the tangent at point A is equal of that angle theta is the derivative at that point xo, yo. And the interval is x minus xo. And the approximation meant that y is approximately equal to y sub 0 plus delta x multiplied by tangent theta. So this is called the linearization equation. Y is approximately equal to yo plus delta x multiplied by y prime, the derivative at o. This linear approximation is anchored on using the projecting angle theta in extrapolating the value of y. This extrapolation will inevitably incur an error of e. Let's redraw the curve showing the tangents at x, y, and x0, y0. That's point A and point B. Draw line connecting point A and point B, that's xy and x0, y0, forming an angle gamma. We see the three angles theta, beta, and gamma. And it is obvious that theta is greater than gamma and also greater than beta. So gamma is somewhere in between. From mean value theorem, if the function is continuous in this interval AB, there must be a point on the curve whose tangent line is parallel to angle gamma. We shall call this point as xm. If we use the derivative at this point, we call it y prime at xm, then we can say that y approximately equal to y0 plus delta x multiplied by f prime at xm. And for approximation, we can only guess more or less what this value will be. As this is a mean value, we can use the arithmetic or geometric harmonic means of x and x0, or a combination of the means, if it's practical to use. Not only can we use the mean of the x0 and x, the tangents at these points may also be average. Thus, y prime at O and y prime can be used to get y prime at M. Therefore, Newton approximation will be transformed into y approximately equal to y sub 0 plus delta x multiplied by y prime, that's the mean y prime. So y prime approximately equal to y sub 0 plus x minus x sub 0 multiplied by y prime at xm. Since y prime m or y prime at xm contains the variable x, the resulting formulas will therefore be nonlinear in nature. Since the projecting angle will be in between the interval AB, these nonlinear formulas are expected to yield much more accurate approximations than linear formulas. Jokingly, we can better approximate a curve by using French curve than using a straight edge ruler, unless of course if the curve is a straight line. Let's start the demonstration of the concept on the classic approximation of the square root function. We will start with the projecting tangent. For Newton-Raphson method, the tangent used was y prime at 0. The other tangent is at point B and will just be called y prime. Starting with the arithmetic mean of the tangent, y prime m equals to y prime at O plus y prime divided by 2. That's the arithmetic mean of the tangent, in which y prime at O is equal to 1 over 2 square root of xo. And the y prime is equal to 1 over 2 square root of x. So therefore, the average y prime equals to 1/2 multiplied by quantity 1 over 2 square root of xo plus 1 over 2 square root of x. And you'll get this 1/4 square root of x plus square root of xo divided by square root of x times square root of xo. This is an approximation, but I will take the liberty of using the equal sign in these formula derivations, as I'm not used to writing so many squiggly approximately equal symbol. Y equals to y sub 0 plus delta x y prime m. Therefore, y prime m, as we found before, is equal to 1/4 square root of x plus square root of xo divided by square root of x times square root of xo. Substituting square root of x equal to square root of xo plus delta x multiplied by this one, 1/4 of this square root of x plus square root of xo divided by square root of x times square root of xo. So substituting all these things and expanding the formula, you can follow it through and grouping del square root of xo and square root of x. You will have square root of x multiplied by square 4xo plus x minus xo equals to square root of xo multiplied by quantity 4x minus x plus xo. Therefore, square root of x is approximately equal to square root of xo multiplied by quantity 3x plus xo divided by 3xo plus x, obtained by the arithmetic mean of the tangents. Note, the formula is a rational function. Now let's try geometric mean of the tangents, applying this to the square root function, as y prime at O is equal to 1 over 2 square root of xo and y prime is equal to 1 over 2 square root of x. So y prime mean, that's the geometric mean, is equal to the square root of the two tangents, this one multiplied by that one. Simplifying, we'll get y prime geometric means equal to 1/2 of 1 over x to the 1/4 multiplied by x 0 to the 1/4. Substituting into this formula, y is equal to yo plus delta x y prime, the mean y prime. So square root of x is equal to square root of xo plus delta x divided by 2x to the 1/4 times x sub 0 to the 1/4. And if in order to eliminate this 1/4, we square both sides. So we square both sides. So we move this into this side, become square root of x minus square root of xo equals to x minus xo over 2x to the 1/4 x sub 0 to 1/4. Squaring both sides. This is what you're going to get. X square root of x minus square root of xo squared equal to this, the delta x squared divided by this one, 4 become x to the 1/2, x sub 0 to the 1/2 because it was squared. So this is equal to x plus xo minus 2x to the 1/2 x sub 0 to the 1/2. Cross multiplying, this is what you're going to get. And after simplification, you'll get 4x to the 1/2, x sub 0 to the 1/2 equal to 8x xo plus x minus xo quantity squared divided by x plus xo. And the final result is square root of x is approximately equal to 8x times xo plus the delta x squared divided by 4 square root of xo multiplied by the sum of x and xo obtained by geometric means of the tangent. And also this formula is also a rational function. Example, find the cube root of 3 using number 1 Newton's linear approximation, number 2 modified with arithmetic mean, and the third one modified with the geometric of tangent. For linear approximation, square root of x is equal to square root of xo plus x minus xo divided by 2 square root of xo. And this is the classic linear approximation of square root. With x is equal to 3, that's what you're going to find. And your initial value will be set at xo is equal to 4. And with the linear approximation, therefore, square root of 3 is equal to this. And you're going to get square root of 3 is approximately equal to 1.75. The error is this one divided by the square root of 3 times 100. And your relative error is equal to 1.036%. By arithmetic mean of tangent, from the equation that we derived, square root of x is equal to square root of xo multiplied by quantity 3x plus xo divided by 3xo plus x, with x is equal to 3, xo is equal to 4. So therefore, cube root of 3 equal to, square root of 3 equal to square root of 4, multiply quantity 3 times 3 plus 4 divided by 3 times 4 plus 3, which is very easy to remember, equals to 2 times 13 over 15. So square root of 3 is approximately equal to 1.733333. The percent error is this, and this is the percent error, 0.074%. And the last one is geometric mean of tangent. This is the formula that we derived. Square root of x equal to 8x xo plus delta x squared over 4 square root of xo plus the sum of x and xo. Similar, x equals to 3, xo equal to 4. And you substitute in the formula equals to 8 times 3 times 4 plus 3 minus 4 squared divided by 4 square root of 4 times 3 plus 4. So you get 96 plus 1 divided by 4 times 2 times 7 equals to 97 over 56. So you get this square root of 3 approximately equal to 1.732142, etc. So calculating for the error, this is what you're going to get. 0.0053%. Comparing the error of the 3 method, Newton 1.036%, the arithmetic mean 0.074%, the geometric mean 0.0053%. If you compare this error to that error, this to that error, that means the geometric mean is 195% more accurate than the Newton. The arithmetic mean is 14% more accurate. And here are some of the formulas that I derive with these different functions. And this is with the arithmetic mean of tangent. This is the geometric mean. And for the square root of x, this is the formula. For arithmetic, this is for the geometric, as we already seen before. And for cube root, this is the formula. Cube root of x equal to cube root of x of 0 multiplied by square root of 5x plus x of 0 divided by 5x of 0 plus x. And for the geometric mean, this is the equation. Quite long. 3x sub 0 raised to the 2/3 plus square root of 9x sub 0 to the 4/3 plus 12x sub 0 to the 1/3 times delta x divided by 6x sub 0 to the 1/3. And this formula, because it contains a square root sign, then in order to avoid this, we can use this one, substitute this into this one, so that in order to not use the square root sign. And subsequently, using this to modify this one, we can get the cube root of x is approximately equal to x of 0 cube. Cube root of x of 0 multiply quantity to 2x plus xo divided by 2xo plus x. And for the geometric means, I simplified this one into this one. Is equal to xo to the 1/3, quantity 6.07735, quantity 1 times quantity 1.4691 n plus 1 divided by 4n plus 11. So what is this n? N is actually, in order to simplify things, n is actually the ratio of x and x sub 0. So x is the number you want, and x sub 0 is the nearest perfect cube. So with using n, then it will simplify things. And this formula is a formula used to calculate any root approximation of any root n. So x raised to the 1 over n, that's the root, approximately equal to x sub 0 raised to the 1 over n, multiplied by, the coefficient here is 2n minus 1 times x plus 1 divided by 2n minus 1 x sub 0 plus 1. Quantity raised to the 1 over n minus 1. So here we can see from here, when the cube root is 3, right? N is equal to 3. So what you do is, this is 3 times 2, n. 3 times 2 minus 1. That's what you get, 5. See? 3 times 2 minus 1, that's the 5x plus 1. This is also 5x, that's for cube root. Minus 1, that's 5x sub 0 plus 1. The quantity raised to the 1 over n minus 1. As for cube root, it's 3 minus 1. Therefore, you get a square root here. So if you want to find the 100 root of x, 1 over 100, if you know this number, x sub 0 raised to the 1 over 100, right? You multiply it by, what is this number? That's 200 minus 1, that's 199. 2 times 100 minus 1 is 199. So it's equal to 199 x plus 1 divided by 199x plus 199x sub 0 plus 1. All raised to the 1 over 99. 100, that's 99. Oh, this is 199. 199. This 200 minus 1. 200 minus 1. This is 1 over 100 minus 1. That's 1 over 99. So the problem with this formula is how to find this one. Especially if your number is big. Like x to the 1 over 100, right? 100 root. This is easily solvable. But this is the problem. If you able to find a near approximation to that number. But anyway, the next function, ln of x, for arithmetic mean, ln of x is equal to ln of x sub 0 plus x squared minus x sub 0 squared divided by 2x x sub 0. And for geometric means, is equal to x ln of x sub 0 plus x minus x sub 0 divided by square root of x sub 0. So for e to the x equals to e to the x sub 0, that's the initial value, quantity 2 plus delta x divided by 2 minus delta x. And for the geometric mean, geometric tangent is equal to e to the x sub 0 divided by 4 multiplied by quantity delta x plus square root of delta x squared plus 4. All this squared, then multiplied by this e to the x sub 0 divided by 4. And for sine of x is equal to sine of x sub 0, that's a known sine. You know, those sine degrees like 15, 30, 45, 60, 75, 90. Those are the x sub 0s. So is equal to x sine of x sub 0 plus delta x multiplied by pi divided by 360. Multiplied by quantity 2 cosine x sub 0 minus delta x pi over 180 sine of x sub 0. So this x sub 0 are all the values that you know. Let's say sine of 35, right? So if you want to find sine of 35, that's equal to sine 30. That's a known value. Multiplied by 5. That's delta x because it's 5 degrees, 35, 30. 5 pi divided by 360 multiply times 2 cosine 30 minus 5 pi over 180 sine of 30. So that's for the trigonometric function of sine. For cosine x, it's almost similar to the sine x, except there's a minus here. So cosine x is equal to cosine x sub 0 minus delta x pi over 360 multiplied by 2 sine x sub 0 plus delta x pi over 180 times cosine x sub 0. And geometric mean, I find it not very convenient to work on this. And for the tangent x, for the arithmetic mean, tangent x equal to tangent x sub 0 plus 4 delta x pi over 180 all divided by 2 cosine of x sub 0 minus delta x pi over 180 sine x sub 0 quantity squared. And for the geometric mean, tangent x sub 0 plus almost similar 4 delta x times pi divided by 180 divided by cosine x sub 0 multiply quantity cosine x sub 0 minus delta x pi over 180 sine x sub 0. See, note you have a square here but you don't have a square there. Because as in geometric means, you know, the derivative of tangent x is 1 over cosine square x. So that's how it's convenient to use the geometric mean in finding the modified form of this formula. So note that x sub 0, delta x are all in degrees because we already included the pi over 180 here. Going back to the approximation of the square root of x using the modified by geometric mean of tangent. This formula 8x x sub 0 plus x minus x sub 0 squared over 4x squared of xo times x plus xo. I only later found out that actually this formula is actually the third iteration of the Newton-Raphson method. The value you can get from here using the initial value for the Newton-Raphson, this is equal to the third iteration. So one formula is already equal to the third iteration of the Newton-Raphson method. Thank you.